So, Katie, I'm just going to start out by telling you the truth, which is that you have almost a 0% chance of helping me understand this. Like, when you were describing black holes, I felt for the first time that wondrous glimmer of understanding that we seek in this world, where I believed you, you know? And I understood that there are these strange, light-sucking, information-destroying maybe things in our universe, and that they're common. And that's wild.
It is. Absolutely.
But now you're about to tell me, look, it's hard enough for me to believe and understand that I'm on a rock that's orbiting a star that's one of hundreds of billions of stars, many of which are orbited by rocks similar to mine, that's in one galaxy, which is one galaxy out of hundreds of billions of galaxies, and that there's more stars in the universe than there are grains of sand on all the beaches on all of the earth. That is hard enough. That's a lot of stuff to try to get my head around. And you're about to tell me that all of that stuff combined is what, like 15% of stuff?
15% of matter, yeah. Yeah.
And the other 85% of matter is stuff that we can't touch or smell or interact with or know anything about except through inference.
You're already there. You're telling me that I can't convince you, but you already know the whole story of dark matter.
I definitely don't, because I don't. That seems utterly impossible, man. It is hard. It is hard enough to grapple with how much stuff I can see. So as you just heard, today's episode is about dark matter, and I'm going to be honest with you, there were moments during this conversation when I started to question my understanding of extremely basic concepts. For example, in about 90 seconds, you'll hear me learn what's actually happening when I pick up an apple. But I left this conversation with a great appreciation for folks like Dr. Mack and the enormous amount of effort it takes to learn pretty much anything about our universe, for the complex journey that scientists embark on that we often don't learn about until it's over and there's a shiny new discovery to show for it. That process can be frustrating and fascinating, and to my surprise, can sometimes involve digging around old shipwrecks for experimental materials. Here's our conversation.
The way that we see regular matter is through interactions with electromagnetism. So you have an atom, right? And the atoms are combined into some kind of solid thing. Let's say you're looking at like an apple or something, right? Like you're seeing that because there is light that's reflected off of that into your eye. So it's able to reflect light. If you held it in front of a light, you would see that it would block out some of that light. So it's able to absorb light. And if you put it in a totally dark room and then like looked at it with an infrared camera, as long as it was a little bit warm, it would emit a little bit of light, right? So it's able to interact with light in a number of different ways because it's made of atoms, and atoms interact with electromagnetism because the light can interact with the atoms in that object. The light can kind of bounce off of those atoms, can be absorbed by those atoms, can be emitted by those atoms because those atoms have electrons on them and protons, and so there are all these electromagnetic interactions that are occurring. So it interacts with the electromagnetic force.
Okay, fine. I get that. Yes. I realize the fine sounded a little judgmental, but I'm already getting anxious.
Okay.
But there are other ways I can interact with an apple. I can touch the apple. I can smell the apple. I can step on the apple.
All of that is still electromagnetism, though.
No, is that true?
Yeah, because when you touch anything, what you're doing is you're pushing the electrons in your hand against the electrons in that thing. When you pick up the apple, it's because your electrons can repel the electrons in the apple such that your hand won't pass through.
Okay.
And so it's electromagnetism that's allow you to touch that thing. Taste and smell are other interactions of the chemicals in the object, sort of interacting with the receptors in your body. And that's also some kind of electromagnetic thing happening, because those are atoms interacting. That's chemistry. That's molecular bonds and things like that, right? So it's all electromagnetism that allows us to interact with things and see things.
Okay.
So if you can imagine, let's say there's a kind of matter that doesn't interact with light. It doesn't have an electric charge. It doesn't absorb light. It doesn't do electromagnetism. It doesn't interact with the electromagnetic force. That's so possible. We actually have already, in a very detailed way, studied a kind of particle that has that property. So there's the neutrino, which is this kind of very sort of ghostly particle. It's produced in nuclear interactions in the sun and other stars. And neutrinos don't do electromagnetism. They don't have an electric charge. They're called neutrinos because they're neutral. And they just don't have any interaction with electromagnetism. They do interact via the weak nuclear force. That's why they can be produced in radioactivity and in nuclear reactions. And they have some mass. So a neutrino has a very little bit of mass, but it has some mass. And we've studied that extensively. We don't know exactly what the masses are. There are 3 different kinds of neutrinos. It's possible that one is massless, but at least 2 of them have some kind of mass. It's small, but it's there. So they interact with gravity. They interact with the weak nuclear force, but they don't do electromagnetism. And that means that they can pass through the Earth without interacting. They can pass through us without interacting. There are trillions of neutrinos passing through your body every second.
Oh, no. like in the movie Ghost, almost.
Yeah, just a shower of neutrinos coming from the sun, coming from other stars.
And it's just going through my body, and I don't notice it. And not only do I not notice it, I can't notice it.
You can't notice it. So because a neutrino only interacts via the weak nuclear force, it has to be a really, really direct hit with another particle to make that happen. The weak nuclear force is a very short-range force, and it's very weak. And so, I don't remember the numbers exactly, but it's something like you could have a light year of solid lead, and a neutrino passing through that has a 5% chance of interacting with anything.
Wow.
So neutrinos pass through your body all the time. I was at a talk once about neutrinos where they were talking about these interaction rates, about the chance of a neutrino interacting with anything in your body in your lifetime. And if it does interact with something in your body, it's it's going to bump an electron, it's going to ionize an atom or something. It's not going to do anything complicated, right? But anyway, you get these interactions very, very rarely. And the statistic they said was, over your lifetime, maybe you'll have 1 interaction with a neutrino.
Wow. Even though there are trillions going through me every second.
Yeah. And I don't remember the exact number of neutrinos going through you every second. Somebody will correct me, but it's
a lot. It's more than 4.
Yeah. And the thing that stuck with me about that talk was they said, and the second one kills you.
But that's a joke, right?
It's a joke.
Just to be clear. Yes. Okay, great. That's an astrophysicist
That's
joke?
That's an astrophysicist joke.
Because I laughed and I was like, that's a funny joke. Yeah. And then I was like, uh-oh.
No.
What if the second one kills me? You say that you can't feel those trillions of neutrinos going through you every minute, but I feel them right now. Ever since I found out about them, I've been feeling them. I feel them very intensely.
That little tingle, right?
So we interact with things with regular matter through electromagnetism, that force that occurs between electrically charged particles. We can see something because light reflects off of it. We are able to touch something because our electrons repel its electrons. But not everything interacts with the electromagnetic force, and because of that, we can't see them, we can't touch them, we can't smell them. They may interact with other forces, like the weak nuclear force, which is involved with nuclear decay, but we humans can't easily perceive that. To us, they might as well not be there at all. Neutrinos are an example of this, as is dark matter. So, if we can't interact with them, how do we know these things exist? Basically, to start off, there are these things called neutrinos that are like ghosts in the sense that they can walk through walls and walk through bodies.
They can go through the Earth.
They can go through the Earth, and they're going through me right now, but I'm fine.
The way we sort of detect neutrinos is there are a few different ways, but the big ways, you take a giant tank of water, you put it under a mountain, and you set up a bunch of detectors around the inside of that water tank, and there are neutrinos passing through all the time. You put it under a mountain so that no other particles can get through, only the neutrinos can get through. And then every once in a while, a neutrino will hit something in one of the atoms of the water, and it'll accelerate that particle. It'll strike it really hard. It'll accelerate that particle. That particle will be blasting through the water now at a speed that's faster than things usually go through water. They say it exceeds the speed of light in water. So it's not going faster than the speed of light as like a limit, but it goes faster than anything can usually go in water because it's just accelerating. And that means that it makes a sort of like the light equivalent of a sonic boom, makes this flash of light. It's called Cherenkov radiation. And then that light is detected by these detectors surrounding the inside of this water tank. We can actually use that as like a telescope because we can tell which direction the neutrino came from because of which direction the flash happens. And it turns out you can make an image of the sun in the neutrino flux, right? So as the neutrinos are coming through, most of them are coming from the sun. So you can actually like make an image of the sun based on where the neutrinos are coming from. And that image of the sun is built up of all of the neutrinos that are coming through, whether it's day or night, if they're going through the earth or through the mountain or whatever. And it's like a fuzzy picture, but it's a picture of the nuclear interactions happening inside the sun. It's kind of cool.
Wow, that's some CSI stuff right there. Like that's like Sherlock Holmes business.
It's really neat, yeah. But anyway, this is a bit of a digression, but the point is that we do know of the existence of particles that act in the way that we think dark matter acts, in the sense that you can't touch it, you can't see it, doesn't interact with light. Maybe once in a while it'll do a weak force nuclear interaction. We don't know. But all of the evidence we have for dark matter makes it look like something that's just a lot like the neutrinos. The reason that we think the neutrinos themselves are not the dark matter is, at least the three neutrinos we know about, there could be other kinds of neutrinos. The so-called sterile neutrino, which is a fourth version of a neutrino that would be heavier and would act a little bit differently, but would have similar properties. But the reason that we know that the three that we know about are not the dark matter is that they're too light. They move too quickly. There are not enough of them to make up all this extra stuff that we know is in the universe. There's just not enough of them, and they move too fast. So they wouldn't be in big clumps where galaxies are. They would kind of disperse too much because they move too fast.
Okay.
But anyway, we do know that it's possible for there to be a particle that just doesn't do light, does have gravity, it does have a mass, and maybe it does something with a weak force. We don't know.
Okay.
So dark matter seems to be something like that. Dark matter seems to be something that we can't see, doesn't interact with light. We can't touch it because it doesn't seem to do electromagnetism, but it has gravity. And it's probably some kind of particle that has a mass, and it doesn't do electromagnetism, it doesn't have a charge. Maybe it does the weak force, we don't know.
Why do we need dark matter to make sense of the universe? How do we know that dark matter is there?
So this is a long story with lots of little pieces to it. There is a lot of evidence for dark matter. When people talk about dark matter in the news, they're usually talking about one particular piece of dark matter evidence, which is about how stars move around in galaxies. So this is the one that's sort of the easiest to explain. So picture a spiral galaxy, okay?
Okay.
The stars are moving around the center of that galaxy. Our sun is orbiting around the center of our galaxy. It takes millions and millions of years, but we go around in a circle. All the stars in the spiral arms they're sort of orbiting the center of the galaxy. And when you picture a spiral galaxy, you have to picture the central part of that galaxy is a lot brighter. There's a bulge of stars. There's a sort of big clump of stars in the center, and then the spiral arms themselves are kind of wispy and thin. Okay, so the way that works is most of the visible matter in the galaxy is really concentrated in that bulge in the center. And the stars in the spiral arms make up a very small fraction of the visible matter in the galaxy. It's mostly in the center. And so you'd expect that the stars that are closer in are going faster and the stars that are farther out are going slower, in just the same way that in our solar system, Mercury goes around the sun a lot faster than Jupiter or Neptune, right? Because it's closer in, so it's feeling the gravity of the sun stronger, and so it has to be going faster to stay in that orbit.
And not get sucked in.
Yeah, not fall in. And then the more distant, like Neptune, if Neptune were going a lot faster, it would just leave, right? It goes kind of slowly and it goes around the sun, but if you gave it too much energy, it would just leave because it's not held on very tightly. Now, in the 1970s, astronomers were looking at the rotation of stars around the centers of spiral galaxies. I think it started in the 60s and 70s. And they were noticing that it didn't seem like the ones at the outside were going a lot slower. When they plotted out how quickly the stars were moving around the center of the galaxy, it really looked like the ones in the center were going kind of fast, and the ones in the middle were going kind of fast, and the ones on the outside were going kind of fast, and it was kind of the same speed. Like all these stars were kind of going around in about the same speed. The person most famous for these observations is Vera Rubin. She's one of the people who kind of made this discovery really well known and really sort of made it very convincing to the community. A whole bunch of people contributed in other ways or did some of these observations around the same time. But the reason there's now a major telescope project named after her is because she was one of the people who was like a pioneer in this field. Anyway, so there was this weird thing where it seemed like the stars toward the edges of the galaxy were going too fast, and they should just be flying off into space. This was even to the very edge of the visible part of the galaxy. Like the farthest out stars you could see going around these spiral galaxies were going the same speed as the ones really close in. And that just doesn't work if just the visible matter is all the matter there is, because it really should be that things have to move more slowly as they get farther out because there's just less matter to hold them in, right? And so the sort of natural inference there is that there has to be more matter than we can see holding these stars in. And it has to be such that, as you go farther out, there's the same amount of like gravity because there's just way more matter. And one of the ways you can do that is if you have a spherical distribution of matter. So their spiral galaxy is a disk, right? But if it's embedded in this giant blob of a spherical distribution of matter where the matter is more concentrated at the center, less concentrated as you go out, turns out the math will work out such that the amount of gravitational force felt by the really distant stars is going to be about the same as the amount felt by the interior stars. And that's because, in this spherical distribution, if you're sort of partway in, you're only feeling the gravity of the stuff interior to you. If you're toward the edge, you're feeling the gravity of all of the stuff.
All the stuff. Yes. Got it.
And we talked about this a little bit previously.
Right. I remember.
And so you can work out the math, and it works out that if the disk galaxy is embedded in this giant spherical clump of invisible stuff, then that naturally explains why those distant stars are moving so fast. Now, one of the things that always comes up when people talk about this explanation is, well, what if we just got gravity wrong, right? Because this explanation assumes that we know how gravity works, and so there has to be extra matter. But what if there's something about when you get to really weak gravity toward the edges of the galaxy, like it's just, you don't have the same weakening of gravity as you go out farther, maybe that law changes. I mean, what we usually have with Newton's gravity, we have what's called an inverse square law. So if you get twice as far away from the gravitational object, the force of gravity is a quarter as strong.
Okay.
So it weakens as the square of the distance, right?
And so if you're 4 times further, it's 16 times weaker.
Yeah.
Okay, I got it. But the argument is maybe that doesn't apply at a galaxy scale. Maybe there's something that we're missing.
Yeah, there could be some weird acceleration scale where like things change as you get to a certain kind of strength of gravity. And this is an idea that's been around for many, many years. The most famous version is called MOND, stands for Modified Newtonian Dynamics. And it was written to just explain this rotation curve thing, to say, well, what if there's just some weird scale that you add to change the law of gravity, and then this all works out with these rotation curves. And you can do that, and you can get the rotation curves to work just as well by modifying gravity. So if you really want to tell the difference between dark matter as like an extra stuff or gravity, the law of gravity changing, you need different kinds of evidence because those two pieces look the same. It turns out that within the solar system, in the history of understanding the solar system, there were two situations where it went in opposite directions around is there extra mass or is there extra gravity? Okay. Are you changing mass or are you changing gravity? And those examples are Mercury and Neptune. The way that we discovered that Neptune exists was that astronomers saw that the orbit of Uranus was weird. It was like being perturbed by something. And they inferred that that could be explained by the existence of an extra planet farther out. And so they did those calculations and they worked out maybe there's some extra planet out there that's messing with Uranus, and they went and found Neptune. There's probably more to the story, but that's the kind of version I know. With Mercury, it had been known for a long time that the orbit of Mercury was a little bit wonky. It was kind of precessing in this weird way. So there were ideas that maybe there was some extra planet near the sun that was messing with the orbit of Mercury. Turns out, no, Mercury's orbit is weird because of general relativity, because Mercury is so close to the sun that the space is really, really curved, and that changes the way that Mercury orbits. So we have these two examples of, changing the matter content in one side or changing gravity on the other side. And so in our solar system, people can argue in either direction about like, oh, well, we have this example. Like, yeah, we have both examples. So with dark matter, the way that things sit now, there are definitely people who still argue, we just need to change gravity. If we find the right way to change gravity, we can explain all this stuff. We don't need dark matter. But the abundance of evidence is very much pointing toward dark matter just being real. Because it's not just rotation curves. There are a huge number of pieces of evidence for dark matter. I'll talk about a few of them. So the first piece of evidence for dark matter actually came even before this rotation curve stuff, when astronomers were looking at galaxies moving around in clusters of galaxies and seeing that basically the galaxies in the cluster were moving too fast. And it was a similar argument to the rotation curve thing, but at a sort of very different scale. And that gave evidence for dark matter.
Because there you're seeing that they're moving around each other as if they had much more mass than they are observed to have.
As if there was more mass holding all of the galaxies into the cluster.
Right. Okay.
So like the cluster, it's kind of like a hive of bees, right? All these galaxies are sort of orbiting around the central region of the cluster, and they're all kind of gravitationally bound in a clump. But if you just count the galaxies, there's not enough matter to account for all of them. In fact, though, in a cluster of galaxies, like most of the visible matter isn't even the galaxies. Most of the visible matter is a bunch of hot gas that's kind of also bound into that cluster from the gravity. That hot gas is just like hot ionized gas that if you look at the galaxy cluster with X-ray telescopes, it's glowing in X-ray light. So most of the visible matter is that cluster gas, intercluster medium is what it's called.
But even with that gas, there isn't nearly enough of it to explain why they're moving the way they are.
Yeah, and the gas itself is another piece of evidence for extra matter because it's so hot that it should disperse. The gas is so hot, there's a lot of pressure and it should be dispersing and it doesn't. It's bound into that cluster in such a way that there has to be extra matter holding that gas in. So that's another piece of evidence that there's more stuff. But then there's also gravitational lensing. So the way that light can bend around massive objects in the universe, we see that, that's very dramatic around like black holes where the light can bend around the black hole and kind of fall into the black hole. But even with just regular galaxies or clusters of galaxies, they can bend the light coming from things behind them. And we can see these we see these really amazing structures in the universe where there'll be a picture of you can find these online where there's a picture of a cluster of galaxies and it's like, a bunch of little bright objects in a sort of clump. And then there'll be these weird arcs around it. These little usually they're blue or red arcs around that cluster, sort of framing it, going around sort of in circular patterns. And those arcs are actually the light from galaxies behind the cluster that's bent and distorted by the gravity of the cluster itself. And the more mass in the galaxy cluster, the more that light gets bent and the more of these arced images of the background galaxies you get. And so that gives you a way of measuring the amount of mass in the cluster because that cluster of galaxies bends space according to its mass, not according to how much stuff you can see. And so that gives you a very objective measurement of the mass of the cluster. And that allows you to tell where the matter is. Even if you can't see the matter itself, you can see how much effect it's having. And you can see that there's a way bigger dent in space, basically, than could happen with just the stuff you can see. And so that gives you a way of also, determining that the extra matter sort of makes sense in this picture. You can see little distortions in background galaxies that kind of give you an idea of the broader distribution of matter in the universe. And that's a subtler effect called weak lensing, but that allows you to really map out where all the dark matter is. And so we've been able to see, if you have two clusters of galaxies, there's a filament of dark matter stretching between them. And we've been able to detect that, even though there aren't a lot of galaxies on that filament, because of the lensing of the distant stuff behind it, you can trace out where that is. So there's all sorts of things like that where we have these indirect measurements. But then there are a couple that are a little bit more subtle, but really important. So, we talked before about the large-scale structure of the universe, right? So how the universe went from being this kind of blotchy plasma in the early times to then those little blotches, the bits of higher density plasma sort of kind of growing up into clusters of galaxies. And I mentioned that you can do simulations where you give the simulation the distribution of matter from the cosmic microwave background, from this sort of blotchy early plasma. You give the simulation that distribution of matter, you turn on gravity, you let it evolve over time, and it creates this cosmic web, this distribution of galaxies on the largest scales in the universe. And I don't know if I mentioned it at the time, but those simulations are done with only dark matter.
Oh, because the visible matter is such a small percentage that it doesn't really matter very much.
Yeah, exactly. So when you do those simulations, when you put in the distribution of matter in those simulations, you just make it dark matter because it makes the simulation easier, because then the only thing that's happening is gravity. If you tried to do that simulation with gas, that gas would have a bunch of pressure and it would sort of resist collapsing. It would bounce off. It would heat up. It would get really complicated. And you can try a simulation where instead of dark matter that only does gravity, you put all the matter in with gas, with pressure and all this stuff. You just can't really form galaxies. It's so much harder to get the matter to come together and create galaxies if you don't have that collisionless stuff. Because when you try and push all the gas together, it heats up and then it pushes out. And then so, you have to find a way for it to cool effectively to fall together. And it just takes much, much longer. If you want galaxies to exist today the way that we see them, you need the dark matter to bring all the matter together and to create this cosmic web. And so these simulations of the large-scale structure of the universe only work if you do have that dark matter component acting as extra sort of glue to hold together all of the regular matter.
So if we do these simulations with the stuff that we see, the world that we see, the world or the universe we encounter with our eyes and our telescopes and our other forms of sensing the universe, it just does not work. But if you make it 85% dark matter, suddenly the universe looks like we would expect the universe to look like. Looks like our universe.
Yeah, or even if you just do the simulation with 100% dark matter, and then when it's done, you say, okay, the places with higher density, that's where the galaxies live. That also works.
Wow. So we can't see dark matter, we can't touch it, but it does have mass and it does have gravity. And even though we can't see it, we can be reasonably confident dark matter exists. There's a variety of evidence, like the way some stars within spiral galaxies move, and even the way some galaxies within galaxy clusters move, based on the amount of visible matter around them. There's a missing piece there, which could very likely be dark matter. And not only does dark matter explain the movements of some galaxies and stars, it also allows us to explain the formation of galaxies to begin with.
We talked about how in the very, very early universe, the whole universe is as hot as the center of the sun, right? And so you have these nuclear reactions. You have hydrogen turning into helium and a few other elements. And we can look at the abundance of elements in the universe, the abundance of hydrogen, helium, and lithium, and a little bit of beryllium. And we can see the abundances of these elements and calculate how that Big Bang nucleosynthesis must have happened. And we can calculate from this stuff how much regular matter there had to have been versus like how much total matter there had to have been for these interactions to occur. And we find that there had to have been mostly dark matter. Like the amount of regular matter is only about 15% of what you would need to get all these interactions to happen and to get the nucleosynthesis to work out the way that we see it. And that's one of the pieces of evidence that is really very hard to argue against, because that's just saying like the regular matter can't be more than a small fraction of the total matter in the universe.
So we have all of these reasonably independent ways, maybe not wholly independent, but reasonably independent ways of looking, obviously not at dark matter directly, but at the universe as we find it. And all of them seem to indicate the same thing, which is about 85% of all matter in the universe is dark matter.
Exactly, yeah. So not only do they indicate that there is more matter than we can see, they all point to about the same abundance of that extra matter and the same behavior of that extra matter. And so, it's one of these things where you're putting together all these different pieces of evidence, and they all match in a way that becomes really compelling when you start to add them up. There's another one I want to mention, just because sometimes people talk about it as the smoking gun for dark matter.
Oh,
and that's even more sort of appropriate because it's a galaxy cluster called the Bullet Cluster.
Oh, that's a good name.
Yeah.
That's much better than Sagittarius A star, which isn't even a star.
It's not a star. No, it's terrible. It's terrible. But yeah, so the Bullet Cluster, the reason it's called the Bullet Cluster is because you had these two clusters of galaxies. One is little and the one is big. And the little one like shot through the big one like a bullet.
Oh.
Sometime, millions and millions of years ago.
Don't want to stop you, but just real quick, that's not going to happen to us, right?
No. I mean, we're going to collide with the Andromeda Galaxy in about 4 billion years, but nothing's going to shoot through us as far as we know. No.
Great. Okay, go on.
Okay, so this little cluster of galaxies like shot through this bigger cluster of galaxies. And the way that we know that is that when we look at these clusters with X-ray light, what we see is that there's a bunch of gas with like a shock wave going through it of like a little bit, like, so there's a clump of gas in one place and then right next to it, there's this little like triangular shock wave where this little clump of gas like, pounded through it and heated up. And so this gas from the clusters got sort of stuck in the middle of this collision, whereas the galaxies themselves pass through because even in a cluster of galaxies, the galaxies are not so close together that if you collide the clusters, they're going to directly hit. They kind of fly past each other, like two flocks of birds. If their birds are spread out far enough, they don't hit in the sky. So the galaxies themselves went through. Most of this cluster gas got stuck in the middle and made this little shock wave that gives the cluster its name. So now it's like a big cluster formed of these two subclusters where they collided in the past, but the galaxies went through, the gas got stuck in the middle. And the reason that this is an interesting piece of evidence for dark matter is because in a cluster collision, what you expect to happen is you expect that the gas will get stuck in the middle because it's this sort of dense plasma gas and it collides and it loses the energy through that collision. It gets stuck, right? It sticks. The galaxies have to pass through because, they're not likely to actually hit and they can go through that cluster gas fine. But the dark matter should go through as well because it doesn't do collisions, right? So if each cluster has galaxies, gas, and dark matter, then what you would expect to see if dark matter is really a thing is that the dark matter should stick with the galaxies, the cluster gas should stay in the middle, right? And we can figure out where the dark matter is through gravitational lensing, through looking at how the space is being bent by these objects. And what we see is that most of the lensing, most of the bending of space is where the galaxies are, not where the gas is in the middle. So if it were just that regular matter had like extra gravity, then the lensing should be in the middle because that's where most of the regular matter is.
Right. That's where that gas is.
Because that gas outweighs the galaxies.
Right.
But the lensing is where the galaxies are, which means it passed through the collision, which means it really is this extra dark matter collisionless stuff.
Right.
And that's something that's quite hard to explain by just changing the law of gravity because you have to move the gravity somewhere else to do that. You have to move it away from where the regular matter is. People come up with complicated explanations that involve sort of a delay of the gravitational force moving, or I don't know. People people try, but it's a difficult thing to explain without just there's another kind of stuff and it doesn't collide.
So the current consensus among most cosmologists is that there is this dark matter, and there may, down the road, of course, be new evidence that causes us to change our understandings of the universe. That's how science works. But that's where we are right now.
Yeah, and the way that I sometimes talk about it is like, it's like if you're walking down the street, and as you're walking down the street, you hear the leaves rustling in the trees, and you look over and the trees are kind of bending over, and the stop sign is kind of waving back and forth, and a plastic bag moves past in front of you, and you feel really cold on one side. You figure there's wind, right? There's all these different phenomena, but they're all consistent with something invisible moving the stuff you can see or affecting the stuff that you can see. And dark matter is kind of like that. We can't see it, just like you can't see the wind, but we can see all these different pieces of evidence that are all pointing to the same explanation.
Right. And we can see things moved by the wind. We can see things affected by the wind, even if we can't see the wind itself. And so when we talk about feeling or seeing the wind, what we're really talking about is feeling or seeing the things that the wind does. I know Dr. Mack dislikes it when I metaphorize science into human experience, but who among us has not been buffeted by forces that, despite being unseen and unobserved, still shape our experience of the world? Like, isn't that the basic human condition? And to over-metaphorize, the future is a kind of dark matter, right? We know it's out there. We know it's most of what's out there, and yet we cannot see it. Anyway, that's why there's life insurance, because life is unpredictable, and so is death, and a good life insurance policy offers a financial safety net to those you love. With Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options are 100% online and let you avoid unnecessary medical exams, so get peace of mind by finding the right life insurance for you with Policy Genius. Head to policygenius.com/crash course or click the link in the description to get your free life insurance quotes and see how much you could save. That's policygenius.com/crash course. Policy Genius, because life insurance is the only rational response to the very strange and somewhat dark matter that is human consciousness. That's a good tagline. I'm just saying. Okay, so to recap, we can assume there's dark matter in the universe from different kinds of evidence. One way is by looking at the abundance of elements in the universe and sort of reverse engineering how much ordinary matter needed to be there at the beginning to end up with all that stuff. Another is by looking at the bullet cluster, where two galaxy clusters collided, leaving a blob of gas in the middle. But instead of the space around it being bent mostly by gas, it's bent more by the less massive galaxies, indicating that dark matter passed through the collision with them. By observing the effects, we find a cause.
We're trying to find ways to detect dark matter where we would get other evidence of it existing in the same way that, like with neutrinos, we found a way to detect neutrinos even though they don't do electromagnetism, by making these giant tanks and letting them interact with the weak nuclear force. And we have a way to detect neutrinos. We would love a way to detect dark matter similarly, but it might not work out. So far, it hasn't worked out. So far, all of the experiments to detect dark matter have been either inconclusive or have found nothing. So there are a lot of different ways that people have tried to detect dark matter. There are kind of three different branches of experiments around dark matter characterization, I would call it, trying to figure out what the dark matter is made of. What is this new particle, if it even is a particle? There's direct detection, which is where you build a detector and you hope that a dark matter particle will come in and bounce off something in a particular way that would indicate that the dark matter came through. So very similar to the neutrino detector idea, but use different detector technology and, it's sort of set up differently. But this is the same idea. You wait for a dark matter particle to come in and interact via the weak force with something in your detector, and then you look for that bump, right? It's called a nuclear recoil experiment. You look for the particle to bump into one of the nuclei of the atoms in your detector. And it's hard because you have to shield against everything else that might bump into your detector. And you can't shield against neutrinos, which should be fine because neutrinos don't add that much energy. And so as long as you set it up properly, it shouldn't be a problem. But if the dark matter turns out to be light enough, or the coupling strength to regular matter is small enough or whatever, you could get to a point where the amount of energy the particle gives your stuff is going to be the same as a neutrino, and then you're screwed.
Right. Then you have no way of knowing.
Yeah. And there are kind of subtle ways to try and get around that by figuring out where the dark matter is coming from or how it changes over the course of the year. But it gets really hard at that point. And we're pushing toward that limit now with these detectors. They're getting really, really sensitive and, haven't seen those interactions. So direct detection is complicated. I should mention there's one direct detection experiment that has claimed a detection, but in a complicated way that most of the rest of the community thinks is probably not valid or just because all of the other experiments disagree. But it has to do with the way that the dark matter signal should change over the course of the year. And they saw basically at certain times of year, because of the way the Earth is orbiting the sun, it's going sort of more into the dark matter, and sometimes it's going more out of the dark matter because of on its orbit.
No way. Seriously?
Okay, so the sun is moving around the galaxy.
Yeah.
And the galaxy is in a cloud of dark matter. Just picture a big spherical cloud of dark matter.
Yep.
And the sun is moving around the galaxy.
Yep. Inside that big spherical.
Yeah. Inside the big spherical cloud.
Okay.
So the direction in which the sun is moving is the direction where it's going to hit more dark matter. The dark matter wind is going to be coming from that direction for the most part. So like if you're driving a car, the wind is coming from in front of you because you're moving through the air.
Right.
So the sun is moving through the dark matter cloud in a particular direction. And at certain times of year, the way the Earth is orbiting the sun, it's going more in that direction. And in other times of year, it's going kind of away. So it's tilted, but in June, it's going more toward the direction the sun is going. In December, it's going more in the other direction.
Okay, so in June, it's headed into the dark matter cloud. In December, it's sort of like the wind is at our back, almost.
Yeah, exactly.
Okay.
And so if you have an experiment that detects dark matter, like you'd expect to see more of it in June than in December. And so there's this experiment called Dama Libra where they don't have a good way of determining what they're seeing. They're detecting some kind of interactions with their experiment, and they're detecting more of them in June than in December.
Mm.
And so their explanation is, well, that could be the dark matter, right? The dark matter could be happening more in June than December, and so maybe that's why we get more flux of something in June than December. The problem is there are a lot of things that can change with the seasons, right? And so it could be some kind of weird systematic effect due to like changes in the atmosphere that affect the neutrino flux, or like who knows, right? Like there's stuff that could happen, things that could change the detector capabilities in some ways. And it's just very hard to know for sure. And so there are now some experiments going on that are trying to test it by doing the same experiment, but in the southern hemisphere.
Oh.
So you're swapping the seasons, but keeping the dark matter wind the same.
Right.
So there's an experiment that I've been involved with called SABRE. They're doing two experiments. They have one in Australia and one in Italy. And they're going to try and do the same measurement with the same kind of detector on opposite sides of the world to see if they have high flux at the same time of year or the opposite time of year, or if they just don't see anything at all.
If they both have high flux in June, that would maybe indicate that it could be more likely to be dark matter.
Exactly. Whereas if the one in Italy sees it in June, but the one in Australia sees it in December,
it's probably seasonal.
Yeah, it's probably seasons.
Right. Wow, that's so cool.
Yeah, it's really neat. There's even weirder stuff around dark matter detectors. So one of the problems with dark matter detectors is that you really have to reduce the backgrounds, which means that you just have to make sure that there is nothing going to come in and bump into something in your detector. So one way is you put it deep underground, you put a bunch of shielding around it. But like even the shielding, if it has any radioactivity in it, it can be a really big problem, right? Because that radioactivity creates neutrons that bump into your detector, and those neutrons look just like dark matter to the detector because they're electrically neutral and they just bump into something, they have some mass. And so, like, radioactivity is a really big problem. So, you know, you have to go around and measure all the radon and all this kind of stuff in your detector. And it turns out that iron that is made or, like, smelted or whatever after the atomic bombs happened has more radioactivity than the stuff that's made that was smelted before it.
Wow. So wait, do you have to try to find like old steel?
Yeah, so people go out and look for shipwreck steel.
Wow.
Like, so there's this like cottage industry of going out and like salvaging shipwrecks to do dark matter experiments.
Man,
because you need the low background.
That's wild.
Yeah. And like there are sort of rumors about certain experiments where maybe they got that steel like not fully honestly. but
it's like problematic steel.
Yeah.
Okay.
Because you had to get so anyways, shipwreck steel is a thing. It's like you try to get really old steel so that it doesn't have as much background, and there's like a limited amount of it, and you know people have to excavate to try to do that. Anyway, it's wild.
I can't believe that you waited 45 minutes to tell me that there's special shipwreck steel that gets used in these experiments.
Yeah.
What other amazing secrets are you hiding from me?
I mean, physics is full of these little things where like you start to dig into something and you find something just utterly wild went on.
Yeah.
You know, all of these experiments, you know, they're happening in the real world, and there are practical considerations that you have to deal with. Like the fact that LIGO, the gravitational wave detectors, there are 2 LIGO sites, and they're kind of out in the middle of nowhere, you know, in their respective places because they need to be like, you know, seismically isolated and all of this stuff. And I mean, for one thing, they can detect the waves lapping at the ocean. The seismic detections are so careful, but they had to put a concrete barrier around at least one of them, and maybe both, but they had to sort of cover the tube with concrete because people were like shooting at the vacuum tube.
Like shooting guns at it?
Yeah.
Oh, that's a bummer.
So they had to encase it in concrete so that the experiment wouldn't like implode from people shooting at it.
Wow.
Yeah.
All of this is a reminder to me that we're on a planet and we're humans and we're doing our best, but sometimes we're also doing our worst, as in the case of shooting up a
gravitational wave detector. Yeah.
It just reminds me of the essential humanity of science, which it's easy to forget about. It's easy to see it as something that like isn't done by or for humans. But we're doing this. Not me as much, but we in the larger sense.
Yeah. I was going to tell you about the 2 other ways that we try to figure out what dark matter is.
Great. Tell me about the 2 other ways we try to figure out what dark matter is, aside from this sort of direct observation strategy.
The way that comes up the most in astronomy is called indirect detection. And I should say that like direct, indirect, these are all kind of relative terms, right? Because you're never going to actually see it because it doesn't interact with light. So even in a detector, what you're detecting is like the motion of something else due to the interaction.
Yeah, you're detecting the leaf shaking in the wind, not the wind.
Exactly. And is that more direct than detecting the motion of stars around a galaxy or the bending of space through gravitational lensing? I don't know, right? I don't know. But anyway, these are the terms that we use. So direct detection is where you use a detector. Indirect detection is what happens when in astronomy, if the dark matter is doing something interesting other than just gravity, something interesting in a particle physics sense other than just gravity, then we might be able to see the effects of that in the sky. So one example, and the most common example for indirect detection, is it's possible that dark matter could be its own antiparticle. So antimatter is
no, wait, whoa. Dark matter isn't antimatter?
Dark matter is not antimatter in the way that we think about antimatter in general.
Okay, great. I was going to ask that question, so I'm glad we got to it. All right, okay. There's something else called antimatter.
Yes, yeah.
Got it.
So antimatter it's a kind of matter that is in some way like a mirror image of regular matter.
Okay.
So, for example, there's the electron. The electron has a negative charge. There's also a particle called a positron, which is the antimatter version of the electron. And it's just like the electron, except that it's got a positive charge and in some sense like spins in the other direction, something like that.
But is it matter?
It's matter in the sense that it has mass.
But what is anti about it?
So the anti is that the charge flips.
So it's anti because the charge is different.
Yeah, and there's a sense of the like spin will be the opposite or something.
The spin will be different.
Yeah.
But it still has mass, and we can observe it.
Yes.
Okay.
Yeah, and that idea that it still has mass, this is something that was actually only recently like really strongly proven.
Okay.
So there's an experiment at CERN where they make anti-hydrogen and they drop it and they see if it falls in the same way as regular hydrogen, and it does.
Okay.
But that was not 100% certain. That was assumed, but it was not 100% certain.
Okay. So a positron has the same mass as an electron.
Yeah, yeah.
Anti-hydrogen has the same mass as hydrogen. It just has opposite charges and spins.
Yeah, yeah.
So dark matter is its own antimatter.
Maybe.
In the sense that it doesn't have a charge.
It doesn't have a charge. Right.
So does it have a spin? We don't know.
Yeah, we don't know.
Is it a little more complicated than the way I stated it?
It's more complicated than saying it has the opposite spin.
Of course.
It has the opposite parity. It's kind of like a mirror image version where
I'm gonna stick with my thing.
Okay, that's fine. Yeah, no, I mean, because I said spin also. But it like parity has to do with like sort of which way it goes in a way that's more subtle than just spin.
Okay.
But it doesn't really matter.
Well, certainly not to me.
Yeah.
But it matters to astrophysicists.
It's to some level, yeah.
Okay.
So the sort of defining feature, the most interesting feature of antimatter is that if you take a particle and its antiparticle and you put them together, they will annihilate.
Like they cease to exist?
Like they turn into energy.
Oh, okay, great. So if you take antihydrogen and hydrogen and you put them together, they are not anything other than energy.
They explode, basically.
They explode.
They would turn into gamma rays.
Can you make bombs this way? Because I'm surprised we haven't.
So in Star Trek, the engines are run through antimatter-matter combinations, right?
Okay.
I mean, this is a
right.
common feature in science fiction that you have matter-antimatter interactions that create your energy because it's the most efficient thing you can possibly do. Because if you take an electron and a positron, the antimatter particle of the electron, if you combine an electron and a positron, they both weigh 511 kiloelectron volts. That's the measure of energy of the mass of these particles. Then you'll get exactly that amount of energy out.
So it's basically lossless energy creation.
It's 100% efficient energy creation. Yeah.
All right. Cool.
So it's the biggest kind of explosion you could possibly do. The reason that we don't use it for energy is because it's quite hard to contain. And so first of all, it's quite hard to create antimatter. You have to have some kind of high energy experiment that'll create the antimatter because that's not an easy thing to do. It doesn't just kind of exist everywhere. But then also you have to contain it. And that's hard to do because if it touches the wall of your container, it annihilates, right?
Right.
So that's not straightforward. And in science fiction, losing the antimatter containment is the big the big disaster that blows up the spaceship.
Wait, because then could it get out of control?
Well, because then it annihilates with everything, all the regular matter.
So it could have a kind of chain reaction if you created... Okay.
I mean, it's not a chain reaction. It's just that any regular matter it touches...
However much antimatter you have, if it touches regular matter, that regular matter will blow up, which could be a problem for a spaceship.
Exactly.
Okay.
Yeah.
Got it.
Yeah, and I think we talked very briefly in the one of the earlier episodes about the question of why there is anything, and the fact that, like, we think that in the very early universe, the same amount of matter and antimatter should have been created. Mm-hmm. And somehow there was more regular matter created because regular matter is what's left. Because if there were truly equal amounts, then we would just be pure energy, right? Because everything would have annihilated. And somehow there was an imbalance, this asymmetry that allowed regular matter to persist. And now antimatter just kind of happens when there's like a really high energy event and some is created.
Okay.
But it's not like out there just hanging around.
Right. But there was this really high energy event at the very beginning that should have, as far as our current models tell us, created the same amount of matter and antimatter.
Exactly.
Which should mean that we're not here.
Yeah. But we are. We don't know why. So that's a mystery.
We are here, we don't know why, and we're trying to indirectly observe dark matter.
Yes. So back to that. So we know that if you take an electron and a positron, put them together, they annihilate. It's possible that some particles are their own antiparticles. So if this is true for dark matter, then a dark matter particle, if it collides with another dark matter particle in just the right way, then those two would annihilate.
Okay, into energy.
In this case, they'd annihilate into other kinds of particles, high energy particles. So they might annihilate into quarks or leptons.
Okay.
They wouldn't go straight into gamma rays because that would require an interaction with electromagnetism that they don't have.
Which they don't have.
Yeah, but they could turn into other particles.
Okay.
And then those particles would then turn into, eventually they'd turn into gamma rays because they would decay in some way. And so there are a bunch of efforts to look for just like a whole lot of extra energy coming from places where there's a lot of dark matter. So, for example, in the center of our galaxy, we know there's got to be a lot of dark matter in the center of our galaxy. If dark matter annihilates, then there should be a lot of annihilation energy coming from the center of our galaxy. And, whatever it annihilates into, it should eventually turn into gamma rays, just like high energy particles, positrons, something like that. And so there's efforts to look for that. And there's efforts to look for a whole lot of annihilation energy coming from the centers of like nearby small galaxies, dwarf galaxies. Like a dwarf galaxy would be a nice place to look because a dwarf galaxy is a galaxy where it's so low mass that it doesn't have a lot of gas in it, doesn't have a lot of stars in it, because basically they're just not bound very tightly. And so when the star goes off, like goes supernova, it throws a lot of gas out. So they're mostly dark matter, these little dwarf galaxies. And so if there is dark matter annihilating there, then it should be noticeable compared to the other stuff that's going on in those galaxies. It's hard in the galactic center because the galactic center has a whole big clump of stars, a whole lot of gas, magnetic fields, a supermassive black hole. Like there's a lot going on in the galactic center. And it's quite hard to see because we have to look through the whole disk of the galaxy, 26,000 light years of stuff to see the center of the galaxy. So if there's dark matter annihilating there, we have to figure out like what else is happening to know that it's dark matter that's doing that. But that said, there is a weird gamma ray excess in the center of the galaxy, and we don't know how to explain it at the moment. And it could be dark matter annihilation. There's models that suggest that would work out. The numbers would be okay for that. But it could also be a population of pulsars that we didn't know about before that are creating a bunch of positrons that then annihilate with their surroundings and create gamma rays.
Mm-hmm. Okay.
Or it could be some other thing that we haven't taken account of. So it's kind of inconclusive. Some people are pretty well convinced by the galactic center excess. Some are not. There have been other weird excesses of energy in various places, extra X-rays coming from galaxy clusters that have been suggested as a possible sign of dark matter decaying in a different way. There's been an excess of high energy positrons in sort of the solar neighborhood that have been pointed at as a possibility of dark matter annihilation, creating a bunch of positrons. That one's less likely now based on our understanding, but Like a few things like that where it's like, yeah, maybe. But the problem with indirect detection is that you have to really know about everything else that's going on in the universe to be sure that this extra bit of energy or, extra bit of sort of high energy particles or radiation is really something new. And that's tough because there are a lot of things that we just might not be sort of counting correctly. So at the moment, it's inconclusive, but that's one of the things that people look for. And it's sort of related to my research, too, because in my research, I'm looking at the possibility that dark matter annihilation was happening when the first galaxies were forming in these little clumps of dark matter that housed the first galaxies. And that extra energy deposition would affect the gas in those galaxies and change the way those galaxies would evolve. But that's a hard calculation, too, because we don't know a whole lot about how those first galaxies behaved and what was going on in them. And so you have to be pretty confident that you understand all of those processes to be able to say, oh, the dark matter would have had this effect and would be noticeable,
Right. Yeah, it sounds like it's really challenging to kind of sort the noise.
Yes.
And understand, where you can sense a strong signal versus where you're interpreting noise as a signal.
Exactly. So that's kind of where things are at with indirect detection. The final avenue is collider experiments. So if it's true that dark matter particles can collide and annihilate into regular matter, then it should also be true that regular matter particles can collide and annihilate into dark matter.
Oh.
Those should be reversible processes. Mm-hmm. And we have some reason to believe that might have happened in the very early universe where everything was super, super dense and there were these back and forth conversions happening all the time. And then when the universe got less dense, dark matter was kind of left alone and stopped annihilating so much and then just kind of became an extra component of matter. But in any case, this process should go both ways. If you can annihilate into regular matter from dark matter, you should be able to go the other direction. And so there are experiments looking for the possibility that proton collisions in the Large Hadron Collider could be making some dark matter too. And that's a difficult experiment, but basically the explanation is just like you collide these protons together, the detectors at the collision site count up all of the stuff that comes out of that collision. So you create a whole shower of different kinds of particles and gamma rays and, whatever. So if you count up all the energy of all the stuff that comes out of the collision, it should equal the amount of energy you put into the collision.
Right.
But if there's something missing, then maybe you created some dark matter and it just escaped because it didn't interact with your detector at all.
Right. And?
We don't have a signal.
So
there hasn't been any compelling evidence in that direction of like missing energy signatures.
Okay. Well, that bummed me out. You set it up.
I know. It would be nice, but so most of the stuff that comes out of Large Hadron Collider studies around dark matter now are like looking for the possibility of new exotic particles that could be somehow connected to the dark matter, like have their own interactions with the dark matter. But at the moment, there's nothing conclusive there, which is kind of a bummer because one of the most compelling sort of theories of what the dark matter particle could be was something that should have had a bunch of other particles that would have been detected by the Large Hadron Collider, and they haven't been seen. So,
just another reminder that we're in the middle of this. Like we're not in the part of science or the part of astrophysics where we tell you everything that is.
Right.
We're in the part where we tell you everything that we're asking questions about, trying to figure out.
Yeah, exactly. And we don't know where the next step in this process is going to take us.
This is something I think about so much because we always credit the person. Like imagine that there's a circular staircase that goes in every direction and there's a bunch of people just kind of standing in the middle. And everybody has to go to a different part of the staircase and walk up the stairs and be like, no, this isn't the staircase that leads to the next floor. I'm sorry.
Yeah.
And then one person or a few people happen to be in the place, and I know it's not just luck, but it's partly luck. They happen to be in the place where they walk up the stairs and they're like, oh, there's something up here, guys.
Yeah.
And then we give them Nobel Prizes.
Right.
But it's not entirely because they... And I think Nobel laureates would say this, that it's not entirely because they were brilliant. It's mostly because there was this circle staircase and everybody went up a different part of it. And then it turned out that there was only one path forward.
Yeah. Yeah, no, 100%. And those people who went up the correct staircase, like they were watching everybody go up the other staircases.
Yeah.
And it was only because all those other people were reporting back what they did or didn't see that led the person to go up the right way, right? That's how this always works. You know, you see which things are working, which things are not working, and you kind of adjust based on that. It's like a very, very long relay race, and you only give the medal to the person who runs the final leg, right?
Right.
It's a tricky business. I mean, yeah, and I don't know which way it's going to go. Like, I think that, you know, what's really exciting about dark matter research is that there are so many different ways to attack this problem, right? There's tons of different ways to look for it, both in indirect detection and direct detection, different kinds of technologies. And then with colliders, you know, trying to do clever things, looking for particles that might be connected to the dark matter. There's lots of room to be creative. There's lots of room to take a lot of different paths, to do different kinds of science, looking for the same goal. It's a neat field to be in. I really enjoy how many different kinds of science I get to learn about in the effort to understand dark matter.
Well, I, for one, am grateful that you're doing that work.
Thank you.
Not least because I couldn't do it. I will say, after this conversation, I'm surprised to be able to tell you that I think I get something about it. I don't think I get it, but I think I get something about it that I didn't get before. And when I started off in a really negative headspace and told you that you weren't going to convince me because it didn't make any dang sense, it now makes sense.
Good. Excellent. I feel good about that. I'm very happy to hear that.
So, a reluctant thank you.
Thank you very much. I appreciate that. I'm happy to talk about dark matter anytime for any length of time.
Yeah, I have a feeling we could have made this like a 5-hour episode.
Yeah.
So holding, smelling, and tasting an apple are all electromagnetic interactions. And there's a type of matter that we cannot see or touch, and that invisible matter makes up about 85% of all matter in the universe and is key to the creation of galaxies. That was incredible new information to me today, but there was a time when it was also new information to everyone. And those discoveries require people doing a lot of work over a long period of time. And as the high demand of steel from old shipwrecks indicates, that work is still ongoing. As I said earlier, we're still very much in the middle of this process. What an exciting place to be. Next episode, we'll talk about the creation of a galaxy that I'm a big fan of, the one we know as the Milky Way. This show is hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, with music and mix by Joseph Tuna Medish. Special thanks to the Perimeter Institute for Theoretical Physics. Our associate script editor is Annie Fillenworth. Our editorial directors are Dr. Darcy Shapiro and Megan Modafferi. And our executive producers are Heather DiDiego and Seth Radley. This show is a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.